Okay, great. So I am Massimiliano Ancini, an assistant professor at the University of Trento. And we have seen Zol talking a lot about how CLIP and vision language models can help us in different type of setup. I mean, actually a lot, also different tasks, not only for different type of labels. And I want to start my talk with this, so with CLIP. I mean, I guess I don't have to tell you how useful CLIP it is, how many things we can do with CLIP, etc., etc. I mean, you are probably even more familiar than me on this. But an interesting thing that CLIP does, and that we are all aware of, is the fact that you can take it and then ask it to classify, perform classification on arbitrary data sets, right? And you get results that are actually quite good. Like even on fine-grained data sets, sometimes you get good results, not always, but still even better sometimes than training a linear classifier on that. So I was thinking, well, let's try it out. So what if I take an image like this, of this poor web doc, and I take some daemon line that does zero-shot CLIP classification from my face, and then I plug some labels. So I can start by saying the simplest question, right? Is it a cat or a dog? Well, CLIP has no doubt. Like this is definitely a dog. Great. Now, what if I try to go a bit more fine-grained? Is it a dry dog or a wet dog? Well, I spoiled it, but I guess you can see it is also in a sync. So yes, the answer is wet dog. And this is actually the scores that you get if you feed this image on the demo. I didn't cheat. But then I tried another thing. So what if I ask if it's a dry dog or a dog? I guess I wouldn't do this example if the answer was right, so I already showed it. We got that like the output is higher, the score is higher for dry dog. And I mean, this is interesting. Of course, maybe there are some features that make the model think that this is a dry dog, but I mean, it's not the case. And so I must say that with this example, it was hard to find a negative example because CLIP in general is really working. So if I ask for the size, it's working. If I ask for the color, it's working. But despite being a toy example, there are a ton of benchmarks that show that CLIP doesn't really work well in compositional setting. And I mean, CLIP and vision language model. This I put just two examples. One is the Vinogram benchmark on my right, and the other is the Aero benchmark, where they ask really the model to perform very fine-grained compositional understanding. For instance, just to give an example, on the Vinogram, you see that the model has to recognize it's a truck on fire or it's a fire truck. These are, I mean, text-wise, things are very, very close, but visually, maybe not, and semantically. So I won't go in the details of the benchmarks, but I can just report some of their main findings. And I think, I mean, it's interesting that, so for Vinogram, the outcome was that most of these algorithms, when they perform matching, they perform at the level of random chance. Interesting. And then also, I mean, for the Aero benchmark, you see that their conclusion was that really CLIP and vision language models struggle with this attribution type of things and understanding relationships. So I gave you probably a bit of motivation for the talk. I will not talk exactly about these problems, but I will talk about compositional zero-shot learning. So this is probably even a simpler setting, but yeah, it's good to study some of the properties that we would like to have for a classification model in a compositional space. So let's start with the basic thing and on what is compositional zero-shot learning per se. Now, compositional zero-shot learning has a very simple definition. You have a set of classes, object classes, and then you have a set of states or attributes. And what you have during training is that you have some compositions of those. like this. Not everything, but just some subsets. And the point is that you want to use whatever you have during training to recognize at this time compositional things, so wet dog, wet cat, that are both seen but also unseen during training. So there is also, you want to sort of fill the full table and be able to recognize whatever wasn't in your training set. And I mean, it makes sense, no? Like that, you don't want to then train your model every time you receive data for all compositions. It's hard to take data for all compositions, so it's just probably better to build a model that in a static fashion, that of course is the kind of topic of this and the next talk, can generalize to unseen compositions of known objects and states. So why is it challenging? Well, maybe visually it's because it looks something like this. So we have that there are categories that even if they are similar, like the tomato and the banana, when they go from one state to another, their appearance, I mean, is pretty different. Maybe not shape-wise, but texture-wise it is. And also we have, of course, the more extreme and easy to grasp case. So I guess you wouldn't like that the way car and cats become wet are the same, because otherwise we wouldn't drive under the rain, right? And so, like, even if the state or attribute is the same, the change that it provokes on the starting object can be very, very different. And this is why, like, we need to model this compositional aspect of the problem. So I think it may ring a lot of bells to you, because it's like historically there have been a lot of related topics. One, of course, is zero-shot learning, where you want to use attributes and descriptions to classify objects. So you don't have, let's say, a simple name for a label, but actually you have a full vector of attributes, and you want to match your input to that vector. This is related, but here probably attributes are more a tool to classify an object, and we are not looking exactly at how objects and attributes, let's say, relate in the visual space. And other examples are these ones that probably are even closer, where we want to model how on a collection of data on the top, you can find out how objects transform and discover this type of transformations and sort of gradients in that space. And also in the example in the bottom, you actually want to learn to predict a classifier for unseen attributes given a certain object. So this is conditioned on the object. Sorry, this is conditioned on the object. But yeah, you didn't have a striped dogs during training, but you want to exploit maybe striped equines, horses, zebra to understand what a classifier of striped or versus non-striped looked like, and then hope that you can generalize it to unseen objects as well. But this is focused only on objects. Sorry, only on attributes. The article that actually defined this type of setting is this one from Ms. Ratal, where they wanted to recognize both objects and states or attributes when composed. And they proposed the compositional zero-shot learning setting that I just described. Okay, now I talked about the setting, but maybe, and also a bit on why do we want to address it, mentioning the problems of CLIP, but I want also to stress the two aspects of the problem and why we want to tackle it in this way. So we want to tackle it compositionally, and we want to recognize compositions, not only because it's fun, but mostly because it has real-world applications. So how we interact in the environment strictly depends not only on the objects, but also on their appearance. So if I tell you to prepare an orange juice, and I show you these oranges or these oranges, I would guess it makes a difference, right? So probably you would pick the top ones, unless you really don't love yourself. And this is why we want to address this problem composition. I mean, this is a stupid example, but also when we drive, we drive differently depending on the state of the road, et cetera, et cetera. And we want maybe agents to do the same. And also we want the zero-shot learning part because we have a long tail distribution of concepts. I mean, it's true that I put the cat at the very bottom, but maybe cats are not exactly what are missing in the web, but it's true that that images don't follow a balanced distribution, especially across compositions. Okay, I hope I convinced you that this task is interesting. Now let's talk about some strategies. And like, if we look at the problem from a practical perspective, what we want to get is to classify attributes and objects, right? So how shall we start? Well, classifying them separately, right? Why do we want even to care about the compositional aspect of it? So the answer is that while this is maybe a straightforward strategy, it doesn't work well in practice because this assumption is just too strong. Because of what we said before, right? That the way an object appears in a composition, object state appears together in a composition depends on their nature, like the appearance of a state depends on the object especially. So we would like maybe to build a compositional classifier, so something that takes our input and projects it into a compositional label. But this we cannot do because, as we said, there are two sets, a set of seen and a set of unseen labels. And we can build a classifier for the seen ones during training, but we really cannot do it for the unseen. What we might do, though, is find a way to estimate this classifier. And this is the first type of strategies I will talk about. And actually, the estimation is pretty simple. So this is kind of what we want to solve. And what we have is that we take as input the set of states that we are interested in and the set of objects we are interested in. And what we instantiate is a function, let's say G, that takes these states and objects, eventually described by some, word embeddings, whatever, and estimates the classifier. So this is a type of hypernetwork type of thing where you want to estimate the parameters of your model, giving some maybe description of the task or some features in some cases. And of course, the hope is that what you are estimating then is good enough and can correctly classify our input image. Okay, I mean, now the point is how do we implement this function G to make it work? Actually, this is what they proposed in the very first work, from red wine to red tomatoes that I described before. And of course, the image is pretty large, but just focused on this bit, where they do exactly what I described, in the sense that they take as input the objects and the states, and they have this function, this multi-layer perception that predicts a classifier, a fully connected classifier. This is one way of doing it. You can also try to build more complex ways of composing, and this is one example. This is another popular approach, task modular neural networks, where here actually you don't predict a simple classifier, but rather you change the connections of your model. And so they predict whether to activate or not some connections, depending on the input composition that we are interested to classify. Okay, this is the first set of approaches, but if you look at it, there is like one probably issue is that we are not, like, we are exploiting the fact that we have states and objects, but we are not modeling explicitly the compositionality aspects of the problem. And this is maybe the question that I want to show you how to address with the next couple of works, and especially with one, attributes as operators. So here, to make you understand probably the idea behind the approach, if you take this bunch of images of cars, I guess you can, in your mind, build a prototype of a car, right? Maybe it will look something like this, for instance. So a car is an object that has a real presence in the world, and you can really build a mental prototype of it, a visual prototype. What about the states though? So this is sliced as attributes or status. Like it's really hard, right? Because it really depends on what we are cutting and how we are cutting it as well. And so you can get, a mixture of things that actually don't resemble anything concrete. And in this article, what they said is that maybe we can model attributes and objects as something cooperating, where objects are vectors, and the attributes are just operators working on the vectors. And this is how you find the compositions, like by taking your object vector, by taking your attribute matrix and operating on the vector. And you hope, of course, that whatever you learn during training generalizes also at test time. And this is the full framework that they show. I mean, it's just a visualization, maybe. Yes, a visualization of what I just described. So it's really nothing particular. I wanted to stress mostly that here then you can play on the compositionality aspect. So you can explicitly enforce that the vectors that you obtain as output of your object and operation applied via the states actually follow some properties that you impose. And these properties can be, I mean, invertibility, for instance, up in the middle, can be antonyms. So if you take a banana, you make it ripe by an operator, and then you do the unripe operation, you would like to get back to the vector of banana, for instance. And things like this, commutativity, etc., etc. And this is pretty interesting. If you check the paper, they also show how this improve the results as more transformations you impose. And of course, even here you can build other stuff, like there is this SimNet approach that builds explicitly symmetric type of transformation that add or remove things from objects, and these are fully learned. There is also another approach that works mostly on the architectural side, and this is through a graph neural network. So here, the composition is not encoded via loss function or some transformations explicitly, but by the fact that we build compositional nodes in our model, and these nodes actually receive feedback from the single, not only attribute and objects, but also indirectly via the propagation in the graph neural network from related compositions. So compositions showing the same objects or attributes. This approach is also effective, different from the others, needs to know the target compositions a priori. Okay, so to conclude this part, I want to talk also about another line of work, that is to disentangle and compose representations. And so actually the key idea here is, again, on working on top of visual product. And we said that one issue of visual product was that it had a very strong assumption, right? A strong assumption, meaning that we are assuming states and objects to be independent. Well, actually, they are not when they are visually composed. And so given that this assumption is too strong, maybe we can find a way to relax it. And this is like what all these lines of work follow as main idea. And I would say there are probably two ways in which you can do it. One is to say, okay, I take my two classifiers and I make them disentangled, so fully independent, or I try to make it as independent as possible. Now I know that formally coloring doesn't show independency or disentanglement, but stay with me. And this you can do it with a lot of type of objectives. And I mean, you can find a ton of works using causal perspective to address a problem, and like also criterion, as you say, to make adversarial classifiers that are confused, like something that is popular also in domain adaptation, etc., etc. So this is really one way in which you can take your simple two-headed model for compositional zero-shot learning and making it a bit better. Another way is actually to take the opposite direction and say, okay, now I don't want them to be independent, but maybe they can just talk to each other while doing so. And this is what I sketched here, that maybe we can take our state classifier and condition it on the object that we predicted. I mean, why not? Or vice versa. I mean, at the end, if I know the object, it's much easier, right, to predict the state. So why not giving this type of information explicitly to my state classifier? And again, also here, there are a ton of works. Also, I'm reporting some of them. Of course, you can check the literature, but like one way in which you can do this is to via some mutual attention mechanism. And this is actually what I wanted to show here is that these approaches are kind of symmetric. So they do the same on the state and object level. So going through attention mechanisms and imposing some constraints both on the classification of the object, the state, but also the composition. And another way that you can do this is to actually explicitly condition that this is what I was talking about. So for instance, the approach on the left shows how you can actually condition the prediction of the state given the object. And similarly, the one on the right shows a similar type of approach where the features that you extract for predicting objects and states are actually different, and we impose them to be different. Okay, so going to the last part is, of course, if we are done, if this is all what you need to know. Of course, the answer is not, because otherwise the talk would have been a bit short. And I want to talk about how maybe what are some assumptions of these settings that are really not realistic and that you should take into account when dealing with them. And one is this. So if I give you this image of this cat, you open the data set and you have probably that is dry cat, the label, right? I am fair. But I would say that the cat is also sleeping, or appears to be sleeping, or I don't know. For sure relaxing, it's not very nervous. And I would say this is also pretty young. It looks pretty young, you know, and not really a very fat adult cat. And this is a problem, right? So the data sets that I've talked about so far, they assume a single attribute label per object. And this is really not what we find in reality, and relates to what also Zsolt was saying before, that categorizing things is really difficult and can be done at different levels. And now there are works that try to address this setting. For instance, at the level of predicting both like multiple attributes, this is one way. And this is only algorithmic, but there are also data sets nowadays that provide you with some actual benchmarks to test if you are able to predict multiple attributes. And this is actually on the top, there is the visual attributes in the wide benchmark, which we have objects, but we have also multiple attribute annotation. And similar, this is the open attribute detection benchmark that came out recently, open vocabulary attribute detection. And there's also, actually, this focus mostly on the attributes, both algorithmic and dataset-wise, but there are also papers that focused on predicting objects and attributes together. And this is overnet, a pretty interesting one that came out at CVPR this year. There is also another assumption. And this other assumption is mostly related to the output space. So what you have usually in composition zero-shot learning is something like this, where you have training compositions that are known and you can train your model on. But also you assume to know the test composition. So you assume to know which set of compositions in your full compositional space you will face at this time. And this is restrictive, right? Because we are excluding also a lot of compositions that can happen in the real world. And even we make the problem easy because we are excluding also the weird stuff that these compositions can mean. So if you have a classifier acting on two directions and you are restricting the way these two directions are combining, things get easier. I mean, not only from a perspective of problem itself, but to give you some numbers, I mean, these are the benchmarks that you will see, mid states that we have seen so far. Zappos on shoes and material, CGQA, which is let's say, expanded version of mid states. And these are the number of objects and states that you find. And this is the size of the test time compositional space that you assume. And this, I mean, it's very small. Now, Zappos is okay, but the others is very, very small. And of course, I mean, if you are restricting yourself to 4 or 2% of the world compositions, this means that you're making your life easier also performance-wise. And this is what you get. So if you test the state-of-the-art on closed world setting, and you test it on this open where you can include everything, performance decrease. And this is, the metric is AUC, area under the seen and unseen curve in terms of accuracy, and you have a bias, the slides between the two. Okay, so we want to address this called OpenWorld. OpenWorld actually is a bad terminology here, and it's the correct one is the one that Zolt talked about, and also Tyler before, but it's called OpenWorld, sorry. And so here, what will be ideal is that you take this full out of space, and first of all, you remove all this noise. I mean, this is garbage. This is just something that can make our predictions don't work. How can we do that? We can use language tools, but actually, if you try it out, it's not easy. For instance, if you just check language tools, dog is mostly correlated not only with dog, but also with hot dog. And so you can find that attributes that work for hot dog work also for dog itself. But maybe you would like to anyway estimate the feasibility of these random appearing things. And we have been working on this line. We did a couple of works. Now, here the feasibility was estimated on the visual space. The key message is that we used it in 2 ways: to remove unfeasible compositions, but also to maybe filter out the, like, apply some losses that takes these weird compositions into account. We did that here at the output space level. We did it also actually in the graph level that I described before when I described the graph-based approach. As a take-home message, actually, is that this actually helps. So if you, I mean, these are qualitative results that I always find funny, especially the inflated eggs that for the closed world model. So if you train the model without taking into account this full compositional space, you may get weird predictions, like, again, inflated eggs, while actually it's a huge balloon. And you can find a ton of examples. It's fun looking at the qualitative results here. But anyway, this is computationally costly, right? We are predicting in n times n, so number of states and object space is super large. And here it can be good to take back and use our old friend, the visual product baseline, right? Because here we are decoupling the problem. So we are predicting m states and objects separately. So it's a much easier problem by itself. And this is nice, right? We have this sort of divided tempera approach. Now, the problems are that this achieves poor results. We saw this before, we discussed that. And the predictions, we don't know if they make sense because they are not communicating to each other. And actually, we found out that there was a simple way to tackle this. First was to increase the capacity of the model. And it's not surprising nowadays, but if you make the predictors comparable in size to the ones of the other state-of-the-art approaches, already the performance gap is much lower, and account for biases, but this is already taken care of in the evaluation metric. And also we introduced ConceptNet to filter out weird predictions. So we checked if we didn't check if something was on ConceptNet, this very large multilingual knowledge graph, but rather we checked the similarity of ConceptNet number batch embeddings. And that was a good metric for the feasibility of things. And this is the framework that we proposed. As you see, it's visual product. What we added was to filter out unfeasible compositions based on a threshold that actually we didn't even set. It was just 0 because we computed the cosine similarity. And these are the results that you get. Actually, this simple baseline, this green one, is very close to I mean, sometimes it's closer to the closer world performance, let's say. But there is a gap that is very large. Now I'm going to conclude because I'm running out of time, but anyway, we can try to fill this gap with the closed approaches, so approaches knowing the test compositions by improving our models. And this is one strategy. You will see also here at ICCV that there is a paper that works explicitly on this setting. But also we can bring back our friends, no, the visual language models, and we can bring them back. The approach at the top just learns some soft prompts for attributes and objects. The one in the bottom does the same, but with a more structured strategy where you also decompose things. And so, I mean, they can really help in terms of performance, and actually they do. Like the blue bar is the second approach, the one doing sort of structured things, and you see that even in mid states bridges the gap, but doesn't do so in CGQA, for instance. And the clip alone, that is the green thing, doesn't solve the problem. So this confirms the compositionality issues. Okay, to conclude, 3 last bits. The first is, if you're interested in this problem, there are resources that you can check out. Are all GitHub repos with different type of benchmarks, but usually they also contain all the baselines that are presented. There are application opportunities. I talked about classification because it's my focus, but the Dima Damen's group and Azeldoti worked a lot on this topic for videos, especially verb and adverbs and actions. Ferjat, that before was here, has been working on 3D stuff with the same principles. And also there are open problems, like the fact that then we are assuming a static environment while we know that things are dynamic. And there is a linguistic complexity that we are not modeling, right? Like that we can go really into the binogram benchmarks and narrow benchmarks that we discussed before. And this maybe we can improve with pre-training, and Aishwarya will talk about that in the next talk. Okay, thank you. I'm happy to take questions. Okay. Either everything was clear or super unclear. This is not a good sign. So that was the closed word, but non-clip based. It was kind of the same baseline I was showing here for the other results. So just saying that was going, like it can overcome by just using visual language models, etc. You can already surpass the results of methods specific for this setting that don't use visual language models. So I mean, it's understandable, but it's, let's say, not surprising as well if you tune things well. Yeah.
So you talked about for actually doing somehow
Yeah, I think so. The challenge that I see is that the level of compositionality that your model has is hard to sort of capture a priori. Like it's related to what you were saying before about knowing, the classes beforehand, etc. So if you are interested in objects and states, maybe you can make sure. I mean, a stupid thing can be that you can check the saliency maps of some CAM methods, and you check that the object and the attributes belong to the same spatial location, so you are binding them correctly, and you impose it as additional constraint while pre-training, for instance. But that should apply also for other type of tasks or things like actions or stuff like this that are not so easy to handle even at a spatial level. So I'm not super sure about how easy it is to incorporate those. I know that there are works on diffusion models that already try to inject compositionality there while to improve stable diffusion, and maybe this type of principles can also brought into pre-training there. But yeah, it's not trivial at all to me.
Thank you, Jose. Thinking about this filtering process, I mean, one of your papers, what is the risk of confusing unrealistic or unfeasible things with unfrequent things? Along the problem, you are having to pay.
Yes, that's a good point. Yes, yes. So I think that there, yeah, I mean, you are definitely right. I think that the prior that you use to estimate this feasibility should be, I mean, really kind of tailored to that. So for instance, when we did that, we focused a bit on the visual side and on the training labels. So if we, during training, we saw, this is why the first works we did on the visual side, because if you know that during training you have a wet dog, and you know that dog and cats are pretty similar, right? Then maybe the attribute wet or dry, even if you don't see a wet cat in training, they apply also to cats. This is maybe a way that you can transfer it, but it's pretty heuristic. Language-wise, also, maybe there is the same issue that you are not sure if something is really non-present. And actually, I have probably a fun fact here, but if you check ConceptNet, it has wet dog, but it does not have dry dog. Because dry dog, you don't need to state it, right? So it's hard even to find not only things that are uncommon, but things that are not explicitly stated. And this is an open problem. I think there are groups that try now to do it with language models, achieving pretty good results, but still, I think, yeah, it's challenging.